You do not want to be like, okay, now it's finally time for me to make sure I can do algebra. No, you want to be practicing it now. So I don't know if that answers your question. I'm afraid to say just give me the raw derivative because that's not going to encourage you to go simplify. Is that okay?
Yeah. I mean, but how simple do you want us to go?
And it's sort of ambiguous because, you know, simplified in whose eyes? You know, like there is no like, for every problem there is like the perfect simplified form. Like if you looked at any of my homework solutions, sometimes my answers, what I considered simplified, looked a little different than the back of the book, but I looked at them and it was just like, they left it as a negative exponent, I dropped it down. Or I converted it to a radical, they left it as a fractional power. Those sorts of little things, no big deal. But if you look at the two and you're like, whoa, you know, he's wrong, I'm going to go prove it to him, you know. You got to make sure your algebra, you know, at least try and get from point A to point B, right? So if you do what I'm saying and try and get it to match the back of the book, you're going to get more practice with feeling, I guess in your mind, you're going to kind of know what simplified means.
As long as it's like not obvious things, like obviously you can distribute this.
Yeah. Common denominators, things like that. Okay, we are recording, my audio is on, and today is the big day, the chain rule. Okay. All right, so it's kind of like there's a progression with these shortcuts, these rules that we're using. We had the power rule, which was nice. Major shortcut, right? We were very happy about that. Product rule and quotient rule, got to work on that last time. So it's kind of like we started out, the power rule was kind of like we were learning how to crawl, right? And then the product rule and quotient rule, now we're up walking, right? And the chain rule is going to allow us to run, all right? If you can't do the chain rule, you can't run. And in calculus, the rest of the way, we're going to be running. We're going to be running sprints. We're going to be doing marathons. And if you can't do chain rule, you're not going to be able to play. All right? Understand? Okay. So here's the way the chain rule works. And this is always such a challenge for me to teach because there's really like 3 different approaches on how to present this topic to the class. And every student's a little different. Some students will look at one approach and be like, yeah, that makes sense. I like that. I'm going to stick with that. Or they'll look at my other approach and they'll be like, yeah, I like that better. That makes more sense to me. All right? But we all, at the end of the day, want to get to a point where we are doing the third approach. All right? So I'm going to show you 3 different approaches to the same concept. And I'm going to slowly, I don't know how slowly it's going to be, an hour and 40 minutes. I'm probably within the first half hour, 45 minutes. I'm going to try and wean us off the first 2 and get to the third one. Now, the reason I don't go right to the third one is because if I go right to the third one, I usually lose about 20% of the students, and they don't have anything else to do, like to use, so they're just like done. You know what I'm saying? So the first 2 methods are something to fall back on. It's a little slower. It's a little more of a process. The third method is more, you'll see, it's just, it's weird. You'll see. When we do it, you're going to be like laughing of the things I'm doing up here. It's kind of ridiculous, but it works. All right, so look, here's the idea of the chain rule. Let's say we have y is equal to a function f, and normally we'd say f of x, but this time it's going to be a function composed with another function. So we have a function inside of another function. In this case, the g function is inside of the f function. So if you were to be the value x, you would first go through the g function, and then that value would go into the f function, right? This is functional composition. How do we take the derivative of a composition of 2 functions like this? Well, the rule is called the chain rule. That's the rule we use for this. And here it is. It says the derivative of this is going to be the derivative of f. Well, that's good because f's there, right? But inside of f, you're going to plug in, inside of its derivative, you're going to plug in g. Notice that the derivative is only on the f, not on the g, right? Then you're going to multiply, and this is where the idea of chain comes from. It's like this is the first link in the chain, here's the second link in the chain. The second link in the chain is the derivative of the g function. And that's the chain rule. Now you have to see it in action before you can kind of understand what's going on, all right? But that's the rule, that's it. Well, we still have a composition here, but what you're doing is you're composing, instead of composing g, right, instead of plugging g into f like we did here, you're going to plug g into what? The derivative of f. And then after you're done with that, you'll multiply it by the derivative of g.
So you must first solve for g of x, then take the derivative of that.
Let's do one. Because like I say, if I write the rule up here, it looks kind of weird. All right, let's just do one right next to this. And by the way, this is the first method, okay? So we'll even put this up here, method 1. And here's an example to go with it. And I'm going to do the first example that's in the book. And the example is y equals the square root of x squared plus 1. Now remember, we still have the power rule, we still have the product rule, we still have the quotient rule, right? We have all those rules, they're at our disposal. But the problem is with this, it is not any of those, right? This is not just x to powers, right? I mean, you do have x squared, you do have plus 1. You could take derivative of those two, but the problem is it's trapped in a root. So it's not so simple, right? Yeah, can you split this up into 2? Can you split that into 2? No, because you can't split a root if you have addition or subtraction inside. So we are stuck. There's nothing we can do with this. So what I'd like for us to notice right now is that this is composition. We have a function, an inner function, and an outer function. All right? Can you tell me what the inner function is? The inner function. And this is going to be our g of x. What is it? The x squared plus 1. That's the inside function, right? X squared plus 1, that's a nice function. That's just a little polynomial, right? That's a little polynomial function. That's my inner function. I'm going to call it g. That thing gets plugged into an outer function. The outer function is what? Root x, and that's what f is, right? F is the square root of x. So do you agree that if I take this right here and I replace that x right there with this expression, then I will get this, right? Yes. So if I take g and plug it into f, I get that. So I have the composition here. Now according to the chain rule, what I need is I need to take the derivative of f and plug g into it, right? And then multiply that times g prime. So over here, this is kind of like scratch work. I'm just setting everything up. I'm going to just take the derivative of each of these because I'll need these. All right, so let's do the g first because it's easier. Derivative of x squared plus 1, 2x, okay? And the derivative of root x, 1 over 2 root x. All right. Any questions? I'm going to come over here now, and I'm going to write out what the derivative of this is. So let's take our derivative, right, of f, which is 1 over 2 root x, but inside of it, what am I going to plug in? G of x. What's g of x? X squared plus 1. So I'm going to write this down, but instead of putting x in it, I'm going to put x squared plus 1. See that? That's g being plugged into this function. Yes or no? I need to know. Yes? Yes? Okay, so I'm going to write down 1 over 2 root, and then now g goes in there. So x squared plus 1 right there. That's it. That is the first part right here. Then I multiply that times g prime, which is 2x. And that is the derivative. Now, can we clean it up? But the 2's cancel, right? And so you get, what, x over square root of x squared plus 1. There it is. There is the derivative of that function.
Could you actually simplify that and not get x squared x plus?
No, you can't. Remember what I said just a second ago. You cannot split this into two roots. Right? Think about this. If you ever at a point in your life mathematically where you're unsure about whether you can do something, give yourself an example and see if it makes sense. Am I allowed to split this up into root 3 plus root 4? Root 9 plus root 4. Well, what's the square root of 9? 3. What's the square root of 4? 2. So this would be 3 plus 2. That'd be 5, right? But this is really root 13. So is the square root of 13 5? No. So that doesn't work, right? Now, had it been 9 times 4, we can. And it would be multiplication. And that would be 3 times 2, which is 6, but that's 36, and the square root of 36 is 6. So it works that way, but not with plus or minus. So that's it. We leave it. We do not need to rationalize a denominator and like get rid of the roots. Just, that's it right there. So what do you think about that? Is that okay?
I can see it can get very complicated very quickly.
It can. It can get kind of messy. Now, let me ask you, would you like to see another example with this method and do a couple of examples with this method and then switch over to the other method, or do you want me to show you the other method now?
Can we do another example?
You want another example? Same method, just stick to this for a while? Okay, let's do that. I don't want to introduce too much too quick. All right, how about next example? I'll leave that right there. Let's let y be equal to sine squared x. Now remember what I said though. At the end of this all, we want to be able to do this using the third method, which I haven't shown you. All right? So if you take a Cal 2 student right now and you ask them to come do this right now, they are not going to write down f and g and little derivatives of each one and then come to they're not going to do it that way. They're going to do it all in their head. But I'll show you how to do that in a minute. All right? This is our fallback method if we need it. All right? We need to identify that this is composition. Yes and no. I mean, it depends on how you want to look at it. I could look at this as being sine x times sine x, right? And then it would be a product rule. Yeah?
Or you could look at it as sine x, and then the second one would be squared.
I could do it either way, right? Like this notation means this. Agreed? So I'm not going to do the product rule. I'm going to do the chain rule. But to do the chain rule, everyone here has to agree that we have a function inside of another function. Right? So what function is inside? Sine x. And the outer function would be the squared function, right? And if you want to try and think about like how do you determine inside versus outside, just imagine that you were the value of x. Okay? If you were x, what would happen to you first? Would you get squared first? No, you would what? Have the sine of u taken, right? Sine would be taken of that value first. That's the inner function. The outer function would be the next thing that happens, which would be the squaring. Yes? Okay. So I'm going to write down, this time I'm going to write it in a different order. I'm going to write f of x here. Just remember that that's the outer one. And the inner function here is g of x. And what are they? Inside's easy, right? Sine x. But the outer one is the squaring function, right? Just squares whatever you give it, so it's x squared. Now we're going to need the derivatives of each one, aren't we? Okay, so we may as well take those. Derivative of x squared is 2x. And derivative of g is cosine x. If you want, you can almost look at the chain rule as being like kind of a divide and conquer, if you've ever heard that terminology. It's like instead of attacking this big ugly problem, we split it up and we take each piece, and each piece individually is a little easier to do than the whole thing. All right, now let's go. That's all we need. The derivative should be the derivative of f, which was 2x, but we're going to replace the x with g of x, which is, careful, nope, we're replacing it with g, right? So sine x. So it's going to be 2, so I'm writing down this 2x, but that x is sine x. Do you see that? That's this guy with that replaced with this. Some mistakes that I see students make will be this. Here they'll write down 2x sine x. That's a very common mistake. What they did is they said, okay, it's this 2x times this. That's not what it is. It's this function evaluated at that value. So that goes into this, not multiply times it. Understand? All right, are we done? That's this part, right? I still need to tack on times what? Cosine x. Derivative of g, which is cosine x. And that's it. We're done there. Unless you recognize that from pre-cal as being the double angle identity for sine. I don't know if you recognize that or not, but in pre-cal, sine of 2 theta is 2 sine theta cosine theta. So I'm not doing any calculus here. I'm just like using a formula that I memorized to switch it over. Okay, that all right? Let's do another one. I'm going to stick with this method. I'm going to just switch the problem up just a little bit, all right? Just a little. See how it changes the outcome of the problem. Instead of sine squared x written like that, I'm going to write sine x squared. So that definitely changes the problem, doesn't it? Where that 2 is?
Is that inside the argument?
Good question. Is that inside the argument or not? Do I have to do anything to let you know that? Actually, I do not. Okay? Because here's the thing. If I want that to be outside, then I should have written it like this.
Or the other way.
Or this way, which would mean it's not on the x, which is the same as this. If I just put the square there, then it's understood that it's on the x. There's no confusion between this because if I meant this with this, it's my fault. My notation's wrong. This notation is correct for meaning you're squaring the argument.
So we have to take that.
That's right.
The notation.
That's right. This is the right notation. Now, what it means is this. It does mean that. Do y'all see the difference between this and the last problem? What is the inner function? X squared this time, right? If you're x, the first thing that happens is you get squared. So that means the outer function is sine x. The inner function is the g, so that was x squared. And we take the derivative of each one, and then we go back over there and we fill it in. So f prime of x is cosine x. Whoa. And g prime of x is 2x. So those derivatives are the same, aren't they? But this is going to be different. This right here is going to be different. So we're going to look at the derivative of f, which was what? Cosine x. But instead of plugging in x, we're going to plug in what? X squared. So this first factor is going to be what? Cosine of x squared. And I'll throw it in parentheses just because I want to be very, very clear with everyone that that x squared is in the cosine. That's done. Then times g prime of x, which is 2x. And I'm finished. I can rewrite this. I can put the 2x out in front. I just can't put that 2x in the argument, so that would be correct right there. And if you compare that to the previous problem, right, where the squared was in here, it's a totally different answer, isn't it? Totally different. What do y'all think? So far okay? All right. I want to do another one. I feel like y'all are getting this, so I'm going to kind of go for it here. How about this? All right, so I want you to assume here that that x is the variable, a and b are constants. So a and b are numbers, but we're not telling you what they are. But they're fixed, all right? So a is not ever going to change, b is not ever going to change. Let's find the derivative of this. So do you have composition here, multiplication, product rule, quotient rule? What do you have here? Composition. You have a function inside of a function, don't you? Function inside of another function. So the outer function here is what? Sine x. So f of x is sine x. And the inner function, g of x, is, what is it? ax plus b. That's a linear expression, isn't it? This is linear, ax plus b. And I know I'm going to need the derivatives, so f prime of x equals cosine x here. And then the derivative of ax plus b. Close, a, right? Because a is a constant, right? So it's going to come for the ride. Derivative of x is 1. So a times 1 would be a. What's the derivative of b by itself? Because b is a constant, 0, right? So this derivative is just a. Y'all with me? A? And so the derivative of y will be the f function, its derivative, right? Evaluated at g. So the derivative is cosine x. I'm going to put cosine what? ax plus b. That's g getting plugged into the derivative. Then times a. Which I could write as the a in front cosine of ax plus b. I could write it that way, right? No harm in that. Now this comes up often enough that, you know, that's kind of the motivating factor here, why I showed you this. I want to see if you can kind of extend on this now and tell me quickly what the derivative of that is. So your instinct should tell you derivative of sine of something should be cosine of it, right? Which it is. The answer is cosine of whatever was there, right? That's a linear expression. So look, the inside was the same linear expression. I should get cosine of that linear expression, but there's one additional thing that always pops its head out in front. The a is always going to be there. And that's the number in front of the x. So the derivative of that, and I'm not, you could make this table, but I'm just going to write it down. The derivative of that should be negative 5 cosine of negative 5x. So it's kind of what you would think. The derivative of sine of something is itself, is cosine of that something. But then you've got that negative 5 that pops out. Okay. What if I change this to cosine of ax plus b? What's going to change here? This is going to be changed, right? Our f is different. Our f is actually cosine here. And our derivative is negative sine. Yeah, so when you do all this stuff and plug in, you're going to get almost the same thing, but you're going to have a negative. So it should be negative a sine ax plus b. I'll let you work through that on your own, but is that a question?
Unless the inside of the argument was negative, then it would just make it a positive.
It would be positive, yep, exactly. So let me give you one example of this. What if we had up here cosine of negative pi x plus pi?
Pi cosine negative pi sine.
So the derivative of this would be pi
So yeah, it'd be
pi sine
and then that.
negative pi x plus pi. Now this only works, okay? Please make a huge mental note of this. This only works real quickly like that if this is linear. If it's not linear, it doesn't work that way. So let me put underneath here, well, here's the formula, right? Here it is. What was a for us in this problem? Negative pi. It's the thing in front of x, right? Negative pi. If I plug in negative pi right here, I have negative negative pi, which is pi, and then sine of the linear expression, which is this. So the negative and negative became the positive, which I think is what you were referring to. All right. We're still sticking with method 1. I'm going to give us another problem now. I think we're ready to turn it up a little bit. So how about this one? Y is equal to x cubed minus 4x squared plus x minus 5 raised to the, put 2 here for now, raised to the second power. So we know from last class that if that was given to us, we could actually square that, couldn't we? Multiply times itself and do all the multiplication. We get a nice long polynomial, and then we could differentiate term by term. And we wouldn't have to do any sort of chain rule or anything else, right?
Yeah.
But if I change this 2 to 2034, then you're going to give up on that idea, aren't you? You're not going to want to multiply that times itself 34 times, 2034 times. So you pretty much throw the whole idea of using the power rule out the window, right? Yes? So the squared maybe wasn't that much of a deterrent, but the 2034 should be a huge deterrent. So do we have a way of handling it?
Yeah.
Yes. Do you see composition?
Yes.
Function inside of a function. All right. What's the outer function?
X to the 2000.
X to the 2034. Right? That's what it is. What's the inner function? That whole polynomial, right? All that. And so we take our derivative, right? Each one. F prime of x. 2034 x to the 2033. So power comes down, power comes out front, subtract 1 from it. There you go. And then the derivative of g, well, that's a nice polynomial. I can just do term by term differentiation. 3x squared minus 8x plus 1. That's all I need, right? That's all I need. Y prime should be the derivative of the outer function with g plugged in. So here's a derivative of the outer function, 2034, but instead of x, I'm plugging in g, which is x cubed minus 4x squared plus x minus 5, and I'm raising that to the 2033. Then times, because it's chain rule, right? Here comes the chain. The second link in the chain is this piece, g prime. And I need that in parentheses, don't I? Because it's more than one term. It's more than one term and you're multiplying, which means you need to make sure that that multiplication takes place properly. And that's it. Now we won't expand that, and that's it, okay? We're just going to leave it like that. That would be as clean as you would want it, okay? Would want to even try and mess with. All right, so this okay so far? Yes? I'm going to stick with this method. Just for now. Let's see my time. I'm doing okay on time. Leave that there. And let's continue to turn it up a little bit. How about x to the 4th plus x minus 4 to the 7th times x cubed plus x squared plus 1 to the 10th. Now there is a pretty nasty looking polynomial times another one. So this is just one big polynomial, and I want the derivative of it. So tell me what you see. Do you see function inside a function? You see chain rule twice here?
Yeah.
You see like an inner function with an outer here?
Yeah.
That's totally different than this inner and this outer? I agree. What's the operation between them? Multiplication. This is a product rule that contains two chains in it.
So you do the chains within the product?
No, we're going to do the product before the chains. Now let's just look at why. Here's my multiplication, right?
Right.
So what I can say from last class is that the derivative of this, notice I'm not bringing in the chain rule yet, right? I know that the derivative of this should be the derivative of the first one times the second plus the derivative of the second one times the first, right? So let me write that down. It's the first one here. That's the first one, right? But its derivative. So right here in this parentheses raised to the 7th, that's the first function. I want its derivative times what? The second function, x cubed plus x squared plus 1 to the 10th. No derivative on that one. Plus the derivative of the second one, which is x cubed plus x squared plus 1. That thing to the 10th times the first one, which was x to the 4th plus x minus 4 to the 7th. Product rule. Agree? Now, each of these, this one and this one, are both chain rules, and we would need to do those separately on the side as scratch work. All right? Until we get to method 3. At method 3, we'll try and do them all like as we go, but again, we're leading into this. And you've got that formula memorized by now, right? Yeah. Okay, there we go. That's our formula. I'll refer back to it. So let's just do the work that we would need for this one right here. All right, let's do that. I'm going to just write it down up here first. There it is. So do you have an outer and an inner? What's your outer function? F of x is x to the 7th. You have the power function something to the 7th power. The inner function on this one is that polynomial, x to the 4th plus x minus 4. You take the derivative of each one of them, right, to set up your little table here. The derivative of f is 7x to the 6th. The derivative of g is 4x cubed plus 1. Y'all still with me on that? Now, I'm going to write the derivative down right here. The derivative of this, okay, the derivative of it, so if I take the prime of that up there, I should get this, which is the derivative of f, 7 with what plugged in though? X to the 4th plus x minus 4. That's going to be raised to the sixth power, then times g prime, so times 4x cubed plus 1, like that. That's it. That's the derivative. And that is just this, right? And I still have this and plus, and I need to figure out this still, and then I'm going to have that at the end. It's going to be big and ugly, right? So I'm going to come back over here right now, and I'm going to continue writing the answer, because I have this part. It's that. 7x to the 4th plus x minus 4, that to the 6th, times 4x cubed plus 1. But then I still have times this one, x cubed plus x squared plus 1, that to the 10th. Is that enough letters and numbers on the board at one point in time? Right, that's just this part. Plus. Now I need this, right? So I have to go set that up over there and do the same thing. You think you could do that on your own? Yes? Okay, so it will, I'm going to not show that. Is that all right with you, or do you want me to show it? I'm up for whatever. Just write it down? Okay, it's going to be 10, and then x cubed plus x squared plus 1 to the 9th times 3x squared plus 2x. That's that. That's the derivative of this. And then I still have x to the 4th plus x minus 4 to the 7th. What's that? That looks pretty bad. Yeah. That's the derivative, though. All right.
So that those first two, like in the y prime, like the 7, and then the x to the 4th, and then the term after that. So you're using the power rule there, right?
I use the power rule.
I mean, to like when you're taking the derivative of that, like that's basically what you're doing. I mean, that's why you have all those terms, right? Because it's like 7 and to the 6.
Yes, that you're getting it. Yes, that's the third method. We're going to try and do this without writing this down. And if you're seeing that already, that's good.
I just wasn't sure.
Yeah. Yep. All right, that's our derivative. Agreed? Now, this one, this derivative actually has some common factors. Remember, there's a big plus sign right here, right? So let's look at this big expression and this big expression. Let's see what they have in common. Let's see, 7, 10, that's not a common factor. How about x to the 4th plus x minus 4? Do you have that over there?
Yes.
How many of them do you have over there? 7 factors? How many of them do you have here? 6. I'm going to pull 6 factors out. Look, this is like, right now what I'm doing is like if I had 3x squared plus, let's say 3x squared y minus 6xy squared. I'm trying to find things that are in common in both, and I'm factoring them out. And I realize right now that this is equal to x to the 4th plus x minus 4, and there's 6 of those in each, right? 6 of them here. There's actually 7 here. But I'm going to pull what's common, so 6 factors. How about 4x cubed plus 1? Do I have that over here? No. How about x cubed plus x squared plus 1? Do I have that over here? Yes, I have it right here. I have 9 of them here and 10 of them here. So I should be able to factor out how many of them? 9 of them. So I can pull out x cubed plus x squared plus 1. You said 9 factors, right? Is there anything else they all have in common? I think that's it. So since I pulled that out, I now need to put a big parenthesis, or if you like, you can go back a little bit and you can use a bracket, that's okay. And what we're saying is, if I distribute this through this bracket, I should get back what's up here. So I had pulled out all 6 factors out of this first one, right? Which left me with the 7 there, right? This was still there. And then how many of these were still there? I pulled out 9 of them, right? So I should have one of those. So right here I should have a 7. I should have a 4x cubed plus 1. And I should have an x cubed plus x squared plus 1, just a single factor. And you can check it right now for yourself. If I take this whole big chunk of stuff and multiply it times this, I should get back that first piece. This times this. Yes, I'm not done. Now I'm going to say plus. Now I need to create this. So I'm going to need to create the 10, right? So I'm going to have a 10 here. How about this guy right here? It's gone. I factored that out. All 9 of them. It's out there. How about this? Still here, right? How about this one? I pulled out 6 of them, right? So I have 1 still here. X to the 4th plus x minus 4, just 1 of them. Now close the bracket. Now you might be asking, why in the hell would I do that, right? Why would you do that? Because this is an example of a problem where we would want to set the derivative equal to 0. And if you set the derivative equal to 0, if you look at this version of it right here, that's very difficult to set equal to 0. Because you have 2 terms. But by doing this, I can now, it's now factored. I can set that to 0, set that to 0, and then whatever this turns out to be equal to 0. And this one's a little easier to work with because you could actually multiply that together, couldn't you? I mean, it would take you a little while. You could do all your multiplication here. But none of them are raised to like the 6th or 7th power anymore. So that's all doable algebra. Collect like terms. Set that whole monster equal to 0. Okay.
It looks like that might take a while.
It would take a while. And I'm not asking you to set it equal to 0 now. It's just, again, to show you the type of algebra that we're going to need to do. Take this, notice a common factor, pull it out. Okay. What do we do? Do we go to the... Let me do one more, and I think after this one we'll go to the next method. What about y is equal to secant of x sine x over 1 plus x? You might recognize x sine x over 1 plus x. Someone asked me to do that problem to start class. T sine t over 1 plus t. I'm taking that and throwing it into a secant function now. This was a homework problem, but with t's instead of x's. All right, what do you see here?
I see the quotient
You see a quotient, good.
and a product.
Okay, where's the product that you're talking about?
Sine x.
X sine x, good. I see that also. So I see a quotient. I see the product up here.
And then quotient.
And chain. It's, look, this whole thing, right, is living inside of a bigger function, secant. So this is composition. Within the composition, there is quotient. And within the quotient, there is product. It seems like it would be a mess, right? Let's see if it is. In the last problem, we had a product, right? And in the product, we had to do chain twice. In this problem, do we have a quotient, and inside the quotient we're going to have to do chain? Or is it, do we have a chain, and inside the chain we have quotient?
No, it's inside
The quotient is within the chain rule, right? So what I'm trying to get you to see is, can you identify an inner and outer function right now?
Yes.
Yes. What's the outer function? Okay, the outer function is secant x. Let's call that f of x equals secant x. All right, what's the inner function? What's g of x? It's this whole thing, isn't it? It's the whole thing. And when I write it down, as I'm writing it down, I'm going to think to myself, Bobby. No, I don't call myself Bobby. I'm going to think to myself, as I write it down, can I take its derivative? Am I going to have trouble with this derivative or not? And I'm going to say, no, I did that for homework. So that should work out pretty good. But I realized that when I did that for homework, I had to do a quotient rule, and in the quotient I had a product. But I should be able to go from here to here, right? Okay, this one over here, the derivative is clean because that's a formula. It's given to us. It's secant x tangent x, isn't it? And over here, g prime of x, well, should we go through this? I don't want to. We did it at the beginning of class. It turned out to be something like sine x plus x cosine x times 1 plus x plus x sine x over 1 plus x quantity squared. We never cleaned it up all the way, did we? We never
factored out x squared plus x, I think.
They factored something out, yeah. I'm just going to leave it like this, okay? This is like the raw version of the derivative. But again, this is a homework problem, so I would expect you could get it to look like the back of the book. All I did here was quotient rule though, right? Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared, and then there's cleaning up that has to happen. All right, you ready to give me the derivative then of the original function? It should be, look, I am conceding this to you, okay? I am agreeing with you. From here to here is some work, right? I mean, that is going to be some work. I agree. I'm not expecting you're just going to look at that and go, oh yeah, and the derivative is that. You're going to have to work for that piece. But once you have it, you can now come and just apply the chain rule. I need the derivative of f with g plugged in. Be very careful here. What's the derivative of f? Secant x tangent x. And I'm going to plug into this what? X sine x over 1 plus x. Right here and right here. So it's going to look like this. Secant of x sine x over 1 plus x times tangent of x sine x over 1 plus x. That's it so far, right? That's this function with g plugged in. Then times that thing. Sine x plus x cosine x times 1 plus x minus x sine x all over 1 plus x quantity squared. And I think the only thing you could do is maybe just take that for like clean it up and make it look like the book's version. And yeah, it's okay. Questions?
What's the other method?
All right. So let me think about how I want to do this. I might show you method 3 before 2. And the reason why is because method 2 is really only there for people who are really having trouble with this. And it's also to show you how Leibniz did it. Remember there were two calculus people, Leibniz? Using his notation. Yeah, this is more of like Newton's notation. All right, so let's get to the shortcut. And I'm going to start back at the very first problem I did. And I'm going to redo it.
So x squared plus 1 is
Yep.
square root?
We had y equals square root of x squared plus 1. All right, you ready? This is method 3. We're skipping 2 for now. Method 3, which I'm telling you is the place you want to be. All right? This is where you want to get to eventually. If you can't get there right away, just keep doing what I did before, method 1, until you get comfortable with it. All right, so we're still going to look at this as having like an inner and an outer function. We still have to be able to identify that. Everyone see the inner function? X squared plus 1. What's the outer function? Square root. I'm going to start on the outside and work my way in like an onion. Okay? Peel the first layer off, then go inside and keep doing that. So what I'm going to do, I always look for something that's appropriately sized for this. I think I can use my towel here. This is what I use in the homework solution videos too. Okay, that should work. right there. Okay. Y prime. What is the derivative of the square root of a tau?
So
1 over 2 root tau. Right? 1 over 2 root tau? 1 over 2 root tau. Right? What's the tau? What was the tau? X squared plus 1. So I'm going to put that right there. Okay? Understand? Okay. What did we just take the derivative of? What was that outer layer that we took the derivative of? It was the square root, right? I'm done with that now. I'm done with the square root. I'm just going to come up here and kind of mark it out that I've already taken care of that. So I've peeled the outside layer off. Now I go inside to the next layer. What's there? X squared plus 1. What's its derivative? 2x. So just go times the next layer's derivative is 2x, and you're done. That's it. Does that make sense? Don't get mad at me. If I start class with this, I promise you I'm going to lose people, and then they have nothing to go back on to actually work through. Yes?
So chain rule is basically going in deeper.
Yep, from one layer into the next. All right?
So if we had a function inside a function outside a function.
We haven't done that intentionally because I wanted you to see that this method is better for that than method 1, because method 1 starts to look pretty nasty once you have composition of 3 functions.
Yeah, because you're trying to like.
Yeah. Okay, can I move on to the next one we did? What was the next one? It was sine squared x?
Yeah.
Okay, so it was sine squared x, which we all agreed was the same as sine x, that quantity squared. Right? And I want this derivative. All right, so I think this eraser over here is about the right size. Outer function is squared, inner function is sine, right? So I'm going to start at the outer function. I have a blue expo eraser squared. What is the derivative of a blue expo eraser that's being squared?
2 erasers.
2 of those erasers to the first power, right? So the 2 comes down, 1 power up there. But the eraser was sine x. Notice I'm not taking its derivative, right? It was covered up, so I don't take the derivative of it while it's covered up. It just comes down and gets copied, right? Then I say times, that's not a prime, that's a 1. Okay, that was a 1 up there. Times, I've done the squared, right? I've done that already. Move into the next layer, it's sine x. What's the derivative of sine x? Cosine x. And if you check, that's the answer we had before. Like I said, I've done this where I just start with this and then there's nothing, I lose students and there's really no recovering because they don't have anything to fall back on, right? If you don't see this, then, and it's also much easier to watch me do it than it is to do it on your own. It's always like that. How about this one? That was the other one, right? Slightly different. What was the outer function here? Sine of x. Inner function was x squared. So I'm going to start with the outer function. I think my mouse will fit nicely in there. The derivative of sine of a mouse is cosine of that mouse. The mouse was x squared. But then times, I've done the sine, 2x is the derivative of the next layer in. And then just move the 2x out front and we're done. If it seems trivial and easy, it's because it kind of is, all right? If you're following it, great. What was the next one I did? Sine ax plus b? Y equals sine ax plus b. All right, think I'm going to need my towel. Or you know what? No. Laura, may I use your bonus question? We're going to take the derivative of sine of Laura's take-home bonus question. So what is the derivative of sine of this take-home bonus question? Cosine of that take-home bonus question, which was ax plus b. But then the chain rule says multiply now by the next thing in, we've already done that. Derivative of ax plus b is a. That's it.
It's going to make that big problem seem a lot easier.
We're about to see. Let's do that one. I'm not going to do the cosine one. All right, so I'm going to need someone to tell me what it was. Let's do the one that was a product rule.
Okay, it was y equals x to the fourth plus x minus 4, and that's all to the 7th power, times x to the third plus x squared plus 1 to the 10th power.
Now, we did have product rule, right? We saw that we had product rule, and I'm not going to be able to do any shortcut to get me around the product rule. I still have to do the product rule. And when I write this down, y prime, I'm going to have to take the derivative of the first one times the second plus the derivative of the second times the first. Would you like me to write it down again, or you have it in your notes, right? When I take the derivative of this right here, right? The first one, when I go to take its derivative, you know what? I'm just going to write it down, damn it. All right. This would be your next step, right? To write it down like that, derivative first times second plus blah, blah. Okay, now when I come over here to do this, I break out my towel. What if you're at home and you don't have a green towel? What if you don't have a mouse or you don't have Laura's take-home thing? What are you going to do? You could use your hand, all right? Or you could use your finger if it's on a piece of paper. You could say, look, I'm trying to take derivative of my hand, or maybe like my forearm, to the 7th power. The derivative of that is 7 that, good, I like that. 7 that to the 6th power. Are you done? No, you now need to say, I've done the 7th, right? Power. Go inside, take derivative of what's in there. 4x cubed plus 1. Tack that on with multiplication. Are we done with this? It had 2 layers to it, right? We had the 7th power, that power came out, the 6th power was applied. Then we multiplied times the derivative of what was inside, that's here. Now this. Plus, over here. So the 10 comes down, x cubed plus x squared plus 1 to the 9th. So you've done the 10th power, it's come down. Now all of this, take the derivative. 3x squared plus 2x. And then you have this out here. It's the same thing we had before, right? That's the exact same thing we had before. What do y'all think? Practice, practice, practice. Yes?
Could you put a bigger pressure around y equals and then move the exponents to the outside and have it to the 17th power for that multiplication?
The only way you could do that, I think what you're suggesting is somehow make this 17th power out here and put a bracket. The only way that would work is if those were the same bases, but they're not the same bases, so you can't add the exponents. It's kind of like if I have x to the 10th and x to the 7th, I can rewrite that as x to the 17th. I agree with that. But I can't put this and this, I can't put those together because they aren't the same base.
No, it's not having an exponent.
Right? So I can't combine the exponents like that. Good?
I think it's
Yes.
better to talk about in terms of the power rule, like combining the power rule or something, like that way,
Because otherwise, it doesn't make sense, like, we're all just sort of.
How do you mean? Are you suggesting I mention that? Or have I mentioned that?
It would be nice.
Okay. I'm going to.
Okay.
I'm not there yet. It's that it has to fall into a certain form for us to use that. So, okay, everyone's kind of following the little shortcut method 3 though?